All right, so I'm not going to be there for a face-to-face lecture on September 25th, so I'm recording this lecture in my office and we'll post it for our first lecture in Chapter 5. So first of all, I'd like to point out that I've taught the course before and I do have a playlist, Heat Transfer Fall 2017. If you want, you could take a look at that recording. The lumped capacitance method was about 38 minutes, and that's basically the lecture I'm giving right now. So as we move into Chapter 5, Chapter 5 deals with transient conduction. The first two sections of this chapter are very, very important. Read them carefully. It deals with the lumped capacitance method, introducing the capacitor or thermal capacitance, and then we want to justify or find out when we can use the lumped capacitance method. Section 5.3, I would encourage you to skim, if not skip. It's pretty interesting that you can do lumped capacitance analysis with thermal radiation, heating or cooling of an object, as well as with convection only, but the convection is variable convection coefficients. I think it's just beyond the scope of this introductory course in heat transfer. If we do need to account for spatial effects, then we'll pick up there next time in section 5.4. It's a long chapter, it's an important chapter, but this especially is very, very important what we're covering today. Okay, so for the thermal capacitance or capacitor concept, think of an object that is being heated at a steady rate. There's a rate of heat transfer Q into the object. The object is an incompressible substance. It has a mass m, and because it's incompressible, you could talk about C sub P or C sub V, or just drop the subscripts and it just has a specific heat C. If you do include the subscript, it would be constant pressure for, let's say, atmospheric pressure for copper sphere or stainless steel piece of material. Okay, so we're interested in predicting the temperature as a function of time, and it'll start with some initial value of temperature, and if Q is equal to a constant coming in, then it'll just increase linearly with time. So we're interested in calculating the temperature as a function of time, and we anticipate to be a straight line. How would we calculate that? Well, we go to the first law, conservation of energy. We would have that the internal energy is the mass, the specific heat temperature minus T ref, some reference temperature for our system, and then we take the time derivative of that. How is it changing, accumulating energy in the system with respect to time? Well, it's accumulating by heat transfer into it. So this is our first law. And so the change in temperature with respect to time, or the time derivative, gives us the m comes outside, the c comes outside, and the t ref is just a constant, so that goes to 0, and you just get dt d time. So here's our equation. So you would think about the flow of heat into our object gives us or results in an increase in the temperature of the object, and if this is constant, the mass and the specific heat are constant, then it's a constant slope over here on the temperature as a function of time. We take a look at this product of m times c is known to be the thermal capacitance. Well, we get that from an analogy with electrical systems. So let's go ahead and review what we know about electrical capacitor. So here's our symbol for a capacitor. It has a C measured in farad, so that's the capacitance of the capacitor. You have the voltage across the capacitor, so the electromotive force measured in volts, maybe I put over here farad, and then we have the current measured in amps that flows through this capacitor. And remember from physics that the rate of change of the voltage across that capacitor is equal to 1 over the capacitance of the capacitor times the current flowing through the capacitor. This is the constitutive law for the capacitor. So we take a look at that, and we just have this analogy that we had the flow, and then we had 1 over the mass, specific heat, the rate of change of temperature with respect to time. This is some changing of the potential the potential being the voltage, the potential being the temperature, the flow being the current, the flow being the rate of heat transfer, and then we see, okay, this thermal capacitance is M times C. That's our analogy. So we have electrical capacitance analogous to thermal capacitance. And you can think about it, when the mass or the specific heat, the product of those get very, very large. So think of a large block of copper, large block of stainless steel or something. Then you have a very large thermal capacitance, and it's very sluggish to the change in temperature, just like a large capacitor with a large farad measurement of its capacitance. It would be very sluggish to the change in the voltage across it. You have to put a very high current through it to change it rapidly, or a very high rate of heat transfer to change it rapidly. Here's our analogy we had between the electrical resistors and the thermal resistor. So the thermal resistor, we had that the resistance was L over Ka. And now we have some sort of node. Typically the capacitor goes down to a ground, and so the ground would be some reference temperature, and so this is the temperature compared to the reference temperature, and that's our model of thermal capacitor. So you can start building resistor capacitor networks, but let's not get ahead of ourselves. Let's just consider one capacitor right now, but you can have multiple capacitors in a complex system. And that thermal capacitance is the mass, or the mass density times the volume times the specific heat. Okay, well, let's see how we can use this. And we have the lumped capacitance method, meaning I'm going to have an object and I'm interested in how the temperature of that object changes with time. So, but I don't want to consider the temperature at different locations in the object. I just want one temperature to represent the object's temperature, such that the temperature at the surface is about the same as the temperature deep in the middle of the object. They're about the same. But what's different is the temperature of the object is much different than the fluid temperature in which it convects heat. So we initially think of a hot object brought out and dunked at time equal to 0 in a bath. And the bath is, I'll just say it's cool. So here we plot temperature as a function of time, put Ti higher than T initial, or I'm sorry, T initial higher than T infinity. And what does the temperature of my object do as a function of time? Well, it's going to go down, but after a long time, it basically goes to the fluid temperature. So we look at that function, we say, is that sinusoidal, that hyperbolic tangent, is that a y is equal to mx plus b, a straight line? No, it's our old friend, the exponential function. So let's go ahead and derive that governing equation and solve and determine that it is truly the exponential function. So here is our first law, conservation of energy, saying the rate of change of energy in the control volume for the object is equal to minus, because it's coming out and it's convecting out into the fluid. So here it is, mc dt d time. Again, that's the one temperature of my object. We have a convection coefficient area, and then the temperature difference that drives the flow. So we see it's always a temperature difference, so it's convenient to introduce theta. And we see that theta starts off large initially, and as time goes on, what does theta do? Theta is going to go to 0 at large time. So we have our definition of theta. We can take the time derivative of theta. It's just dt d time, dt d time. Okay, and so this differential equation can be modified to be d theta d time is equal to minus HA over mc theta. We can introduce our resistance, our thermal convective resistance, our thermal capacitance, and we get a differential equation, first order, d theta d time is equal to 1 over, or minus 1 over RC theta. So with this initial condition, that theta at time equal to 0 is equal to theta initial, you can now solve. This gives you the easiest solution, the one that you wish was all on the final exam of the differential equation class that you took. It just gives you the exponential solution. So if you want to, you can unravel it and get t as a function of time, t infinity plus t initial minus t infinity, e to the minus t over rc. So this is the equation we had on the previous slide, and we can express it as minus t over rc or minus t over tau. What is tau? Well, you can think of a thermal time constant. Just like we had an electrical time constant, you have a thermal time constant. So if you make the calculation of the thermal resistance times the thermal capacitance, you can prove to yourself that that does have units of seconds, and it's needs to have units of seconds as shown in this equation, and it really is a time constant. With that, we want to now take a look at this function, our exponential function, and just revisit and refresh our memory on that. So theta over theta initial plotted as a function of time going out, and this function starts at 1 and goes to 0. So what we're plotting is this blue line is a plot of e to the minus t divided by tau. And because we've introduced this time constant, it has units of seconds or some time unit, then it's actually good to measure the time axis in units of tau. Let's start at 0 and go to 1 tau, then go to 2 tau, then 3 time constants, and 4 time constants, and 5 time constants. And then you see that if you go out the length of time of 1 time constant, it'll have gone from initial value of 1 down to a value of e to the minus 1, which is about 0.37. So I didn't keep in more digits than that, but your calculator can show more digits. But I would round that off to a third. So 2/3 of the transient is already happened by that time, 1 tau, and about 1/3 is still left to happen. If you go out 3 time constants, then you put in e to the minus 3, and you may remember that's 5%, roughly 5%. Essentially, a lot of engineering systems, their tolerances is if you're within 5% of the steady state value, you basically, the transient has finished. 19/20ths of the action has already occurred, of the temperature change has already occurred. But maybe you need more fidelity, so you go out to 5 time constants. Well, e to the minus 5 is less than 1%. Just use your calculator, verify these numbers, which is essentially there. You basically don't have anything left. The system is gone to 0. So the transient has finished occurring at your new steady state value of theta is equal to 0. Now, if you really have a system, which is rare in engineering, where you need more fidelity than that, then sure, you could think about, well, I think the action ends at 7 time constants or 9 time constants, but I've never found that in practice. It's either the 3 or the 5 time constants. 3 for vast majority of engineering applications, 5 if you really have something where you need a lot of accuracy in this exponential function. So now let's think about the validity of that lumped capacitance method. What we have is sketch a temperature profile as a function of location x. This is kind of going from the center of a center line of a slab, and you have convection on this side at x equal to minus L, and convection at x equal to plus L. And you're looking at sketching the temperature profile. We know if we wait long enough, it'll be the center line temperature is the surface temperature is the fluid temperature. But initially, the center line temperature and the surface temperature all at T initial. And when you dunk it in, it starts to cool rapidly. And so that surface temperature is going to drop. And for some systems, the surface temperature will be much lower than the center line temperature, but some systems, it'll be pretty flat. Interior. Good conducting materials, TS will be close to T center line. But if it has a lot of resistance to conduction within the solid, then TS will be a lot different than the maximum temperature, which would be at the center line. So we want to compare, what about this temperature difference due to conduction within the solid to drive the flow to the boundary. Compare that to the temperature difference to once it's at the surface to drive the heat into the fluid. Well, this is Ts minus T infinity. This is temperature at the middle minus Ts. If this is true, if the temperature difference within the solid is small compared to the temperature difference from the solid surface into the fluid, if that's true, then yes, use the lumped capacitance method, because what the lumped capacitance method says is I only have one temperature for the object and it's a function of time. That same temperature is in the middle of the object as well as at the surface of the object. Well, how do we justify this? We come in and we do an energy balance at the surface right here. We say, what is going into the surface at the left from conduction from the interior, what's going out into the fluid on the right of this little thin control volume at the surface. Well, what's our model for conduction? K A over L delta T that drives it, equal to HA delta T that drives it. And so we can rewrite, and we have an equation now. Hey, there's this delta T conduction inside is equal to HAL over KA, and then delta T convection. What we want is we want this to be very small compared to that. When will that happen? When this ratio is very small. So we introduce the BO number. The BO number is HL over K, or H A times L divided by KA, or H volume divided by KA, or BO number is this H L sub C divided by K, where L sub C is some generalized length scale. It's the volume to area ratio. For a slab, this L sub C is the half thickness, and we'll consider now in the next slide for other radial systems. But when the BO number is much, much less than 1, that is the criteria where we would say the lumped capacitance method is valid. It's justified in being used. Well, what is much, much less than 1 is 0.000001, much less than 1. Vast majority of people say, yes, that's very, very small. It's negligible. How about 0.1? Well, maybe. A lot of engineers would say, yeah, that's close enough to be negligible. And in the textbook, they have a little discussion of this, but basically the cutoff criteria is based on the engineer's tolerance for this approximation, and roughly about a 6, about 0.17. If you're below that, then you can look at starting to use the lumped capacitance method, because it's not perfect, but it is a good model, simple to use, and fairly accurate. Now, if you come in with a BO number 0.5, don't use it. BO number of 1.3, don't use it. It's too high. But the cutoff, again, it's a judgment call. It's around 0.1 or around 0.16, 0.17, around 1/6. Well, here we've introduced the problem for the BO number. We introduced this characteristic length is that half thickness L. Half thickness L when you have a slab and you have convection on both sides. Well, you do the same thing for a cylinder and for a sphere. You just have to remember the characteristic length is some volume to area ratio. For the cylinder, we only have convection off of the sides. L is large, and so you neglect the ends. Neglect the ends for the convection off of the cylinder. And so then you do the volume, pi r squared L, times the area. The area is only this side area, not neglecting the ends, so 2 pi r L. And you make some cancellations. You find that the characteristic length is the radius of the cylinder divided by 2, or if you're working in diameter, d over 4. Same thing for the sphere. But here we don't have ends to neglect for the sphere. It's truly just the volume to area ratio. You put in the area and the volume and you get the radius divided by 3. So these are some formulas that are easy to remember. For a slab, it's the half thickness. For the cylinder, it's radius divided by 2, and the characteristic length in the calculation of the biot number for the sphere is radius divided by 3. Now this is looking ahead into chapter 6, but they do have a table of dimensionless coefficients, and since this is one of the first ones, I thought I'd just point that out. Here's the biot number. They put a H L sub C divided, or just L, I think. I put the C in there, the characteristic length, divided by K, HL over K. Now they do add this S, meaning it's focused on the solid thermal conductivity, not the fluid if you're dunking it in oil or water, not the fluid conductivity, but the solid conductivity. And it's interpreted, just like the Reynolds number has an interpretation, the biot number, these dimensionless groups have interpretations. It's a ratio of the internal thermal resistance to that convective thermal resistance at the boundary layer. Okay, so you can take a look. We're going to move into chapter 6 after we finish chapter 5. Also in this chapter, not today, but we're going to be using the Fourier number. Fourier number is a dimensionless time, and you can have some interpretation of it. Let me not bog down the lecture right now, but I just want to point that out. You can also find the Reynolds number, the RE in this table, and so we're going to be using a lot of these dimensionless parameters as we move into convection. Well, let's solve this problem. We have a solid 3 centimeter diameter sphere. So it's made of copper, and the copper has thermal conductivity, density, and specific heat given. So we put down our diameter. We could use the radius, or we could use the characteristic length as radius over 3 for a sphere, or diameter over 6 for a sphere. Okay, we're given that it comes out hot of a furnace. Its uniform temperature is 80 degrees C. It's abruptly moved to air that has a T infinity of 20 degrees C, so it's going to be cooling in air with this convection coefficient. So initially, the theta initial, the temperature difference, is 60 degrees C. That's what drives the convection off of the sphere. All right, continuing to read the problem, use the following properties for copper, and it then asks how long will it take for the center of the copper to be cooled to 50 degrees C. Well, we're interested in theta at some future time such that the center is 50 minus 20, or the theta is 30 degrees C. So it went from 60 degrees to 30 degree delta T. We would love to use the lumped capacitance method, but we need to verify that it works or is valid. So we calculate the biot number, H L sub C over K. There's our H given, there's our characteristic length, there's our thermal conductivity, and we calculate a biot number of 0.00097. Well, you look at that number, and 99.999% of the engineers would say, yes, that's less than 1, much less than 1. So we want to use the lumped capacitance method. We have now verified that it's accurate because of this low biot number. So this is a reminder of the theta equation with our thermal time constant. We can actually put in numbers for the thermal time constant, calculate that it's 229.2 seconds, or around 230 seconds for that thermal time constant. So manipulating our equation, we know what theta we want it to be. We know it starts at 60. We know what the tau is, the time constant, and we can solve for t. So here's t is equal to minus, don't forget the minus sign, tau natural log of theta over theta initial, just algebra at that point. Stick in our values, and we find that the time that you need to wait for it to cool is 160 seconds. Well, with that, we've wrapped up this lecture. Again, I just stress these are very important. Skip this section, and next time we'll move into spatial effects. Thank you.